You are falling, but not the kind you recognize. There is no drop in your stomach, no rush of cold air past your body. There is no sensation of movement at all. You are simply going. You are moving faster every second, pulled by something you cannot see, drawn towards something you cannot escape. And this is the part that changes everything. You would not feel it, because gravity pulls on every single part of you equally. There is no pressure, no force pushing back against your skin. From your perspective, you are weightless. Everything feels completely normal. But the moment that piece ends, you will not experience it, because by then, the outcome is already decided. From a distance, black holes are extraordinary to observe. Not because you can see them, you cannot, not directly. What you see is the absence, a region of space where light bends around something invisible, where the fabric of space-time curves so steeply that even photons cannot escape. The result is a ring of distorted light, an accretion disk glowing orange and white and gold. Superheated gas spirals inward, moving at a fraction of the speed of light. The first image ever captured of a black hole was released in 2019. It showed M87, a supermassive black hole 6.5 billion times the mass of the Sun. The image was blurry by photography standards, but the shape was unmistakable. A bright ring surrounding a perfect dark circle. Scientists called it a shadow. This is the edge of the place where information ends. It looks from that distance like something beautiful, almost meditative. A glowing eye suspended in darkness. But the closer you get, the more the beauty reveals its truth. The beauty is only concealing what lies within. The danger begins with geometry. Gravity weakens with distance. That is a fundamental property of how mass works in space. It means that if your feet are closer to the black hole than your head, your feet are being pulled more strongly than your head. The difference in gravitational force across your body is called a tidal force. Around a stellar mass black hole, those tidal forces become lethal. This happens before you even cross the event horizon. Physicists call the process spaghettification. The name sounds almost playful. The reality is not. Your body would stretch. You would stretch vertically along the axis pointing toward the black hole. Your feet accelerating faster than your torso faster than your head. The stretching would be slow at first, imperceptible, then measurable. In a period of time too brief to fully process, it is complete. You would be pulled into a thin stream of matter, elongated across thousands of kilometers, still technically falling, still composed of the atoms that were once you, just distributed across a geometry that no longer corresponds to anything living. But here is where the physics becomes genuinely strange. Around a supermassive black hole, one millions or billions of times the mass of the Sun, the tidal forces at the event horizon are actually much weaker. The event horizon of a sufficiently large black hole is far enough from the center that the curvature is gradual. You could cross it without feeling anything unusual. No alarm, no signal, no physical sensation at all. The event horizon is not a wall. It is not a surface. It is a mathematical boundary. The point at which escape velocity exceeds the speed of light. Cross it, and you have not entered a room. You have entered a set of equations that no longer include the word return. You would cross it without knowing. That is not reassuring. That is the most unsettling part. Someone watching you fall would see something different. As you approach the event horizon, the light reaching the observer is increasingly red-shifted. It is stretched by the curvature of space-time. From their perspective, you slow down. Your motion becomes sluggish. The light from your body dims and shifts. It shifts from visible light to infrared, then to something no instrument can easily detect. You appear to freeze at the horizon. Then you fade. To the observer, you never actually cross it. You simply become dimmer and more still until you are gone. From your perspective, you cross in a moment. Time from the outside continues at its normal rate. Time from the inside continues at its normal rate. But the relationship between those two clocks has broken completely. If 1,000 years pass outside, you do not experience 1,000 years. You experience your own subjective timeline falling inward. There is no communication possible, no signal that could be sent out, no way to know what is happening beyond the horizon you just crossed. You are, in every meaningful sense, no longer in the same universe. You are no longer in the same universe as the people watching. Inside the event horizon, space and time exchange roles. This is not a metaphor. In the mathematics of general relativity, the singularity is no longer a place. It is a moment in time. It is your future, an inevitable future. Outside a black hole, you cannot stop time from passing. Inside, you cannot avoid the singularity. Every direction you move leads to the center. Every thrust of a hypothetical engine points to the same fate. The geometry has changed. Inward is no longer a direction in space. Inward is now the direction of time itself. You could try to fire your thrusters. Imagine a probe with sensors still active. It is transmitting to nothing. It is collecting data that no one will ever receive. It fires its engines at maximum capacity. The probe burns fuel in what it calculates as the opposite direction. The instruments record the burn successfully, but the probe continues falling. There is no opposite direction anymore. There is only forward, and forward leads to the singularity. Here is the part that breaks the clean narrative. Everything described so far comes from general relativity. Einstein's framework for gravity and space-time, the large-scale structure of the universe. And general relativity has been tested and confirmed, observed to extraordinary precision. It predicted black holes before we had evidence they existed. It predicted gravitational waves. It predicted the exact bending of light around massive objects. But general relativity breaks down at the singularity. At the center of a black hole, the equations produce infinities. Density becomes infinite. Curvature becomes infinite. And physics, as currently understood, stops producing meaningful answers. The singularity is not a discovered location. It is a gap in the theory, a place where our best description of reality admits something. It does not know what happens next. And there is a deeper problem, one that physicists have argued about for decades. It is called the black hole information paradox. Quantum mechanics states that information cannot be destroyed. Every particle and every interaction, every configuration of matter carries information, and that information must be conserved even as matter changes form. Burn a book, and in theory, you could reconstruct it. You could use the pattern of smoke and ash. The information is preserved. But if matter falls into a black hole, and the black hole eventually evaporates, as Stephen Hawking predicted it would, slowly over enormous timescales, through a process now called Hawking radiation. Where does the information go? Hawking radiation carries no information about what fell in. The black hole evaporates. The matter is gone. The information appears to be gone. This is not a solved problem. The two most successful theories in physics contradict each other here: general relativity and quantum mechanics. At the singularity, they simply disagree. What this means practically is that what actually happens is unknown, not uncertain, not approximately known, unknown. The most extreme environment in the observable universe is also the one we understand the least. There is no version of this that ends differently. Cross the event horizon of a stellar mass black hole. The tidal forces destroy you before you reach it, or shortly after. Cross the event horizon of a supermassive black hole, and you arrive intact, in silence. Falling through a region of space where every direction leads to the same endpoint. Your instruments still function. Your body still functions. The air in your suit is still breathable, and none of that matters. The singularity is not somewhere you can avoid. It is not a location you can navigate around. It is a moment in your future. The geometry of space-time has already determined it. Every second that passes is a second closer to it. Not because you were moving toward it, but because time itself is pointing in that direction. You fall, not dramatically, not in darkness and noise. You fall the way everything falls, because gravity does not ask, and space-time does not negotiate.